So let us see crypt arithmetic. It is a branch of cryptography, where cryptography is the study of breaking codes and encrypted messages. So we will be replacing the original text with some other values so that a third person will not be able to make out anything out of it. That is known as cryptography. The crypt arithmetic is an arithmetic puzzle using letters and digits. We will be replacing the digits or hiding the digits with some alphabets, and we have to find these digits by using arithmetic computations. That is known as crypt arithmetic. Actually, this is a classical example of constraint satisfaction problem. Why? Because we will be using many constraints associated with crypt arithmetic. So here we assign decimal digit to each of the letters in such a way that the answer to the problem is computed. We will be having some alphabets and they will be equated to find a solution, and we have to find a digit corresponding to each of the alphabet present. It will be clear when we see an example. Being a CSP, constraints need to be followed. The main constraints are: we can have any number of alphabets repeated. In the equation, an alphabet can be repeated any number of times. If that is the case, we have to assign the same digit to all of these repeating alphabets. That is one constraint. Then one digit cannot be assigned to different alphabets. These are the two main constraints. There are additional constraints. No two digits can be assigned to the same letter. We have already seen that. Only single digit can be assigned to a letter. That also we have seen. Each letter can take a value from 0 to 9. So only single digits are permitted as values of alphabets. So the domain of each of these alphabets is 0 to 9. This can vary because there are additional constraints for taking these values. So this can vary. Domain can vary based on the alphabet position in the equation. No two letters can be assigned the same digit. That we have seen. Leading letters cannot be 0. Suppose we are having a 3-digit number. It cannot be stated as 0 to 5. Because the equivalent is 25, which is 2-digit. If we want a 3-digit number, the first digit should not be 0. So in that case, where the alphabet is the first one in a some digit number, then the first alphabet will not have this 0 in the domain. It can take only values from 1 to 9. So the domain have different value sets for different alphabets based on the position of the alphabet in the number series. Assumption can be made at various levels without having contradiction. We can have additional constraints based on the requirements as the problem solving proceeds. The problem can be decomposed with available constraints. Any of search techniques can be used here. Only thing is, we have to look into the constraints associated with each of the steps that is being used in that search operation. Then backtracking can be performed we must use, because crypt arithmetic is a trial and error method. So if one value is not matching, we have to discard that and try with another value, which is the basic of backtracking. We are redoing some of the steps with some other values. So backtracking is allowed here. Then rule of arithmetic must be solved. We can have addition, multiplication, division, or subtraction, anything. With the rule of mathematics, we can do this arithmetic or solve these problems. It's a very simple one. Let us see with an example. So crypt arithmetic example. Suppose we are using these words to hide some numbers. She had food. It is not necessary to have meaningful words. We can have any alphabet in any order. So she had food is our masking alphabets. Besides this, or behind this, we have 3 plus 3, 6 plus 4, 10 digits available. Okay. So one possibility is this. If we assign 4 to S, 7 to H, 0 to E, then 5 to A, 3 to D, and 2 to O, 1 to F, this problem is solved. Because 3 plus 0 is 3, 5 plus 7, 12, carry 1, 1 plus 4, 5 plus 7 is 12. So when we are using two H's here is an H, here is another H, they should have the same value. So 7, 7 are repeated, O repeated, they should be same, DD repeated, they should be same. When we are adding two numbers, two 3-digit numbers, this should not be 0, this should not be 0, as well as this should also be not 0, because they are all the starting digit of these numbers. They should be non-zero values. Whenever we add 3-digit numbers, two 3-digit numbers, their sum cannot be more than 2000, below 2000 only, because the maximum number allowed here is 999, plus 999 will add up to 1998. So surely the value of f will be 1 only. The possible values are 0 or 1. Because of the constraint, 0 is not allowed. So value of f should be 1. So we got a 1 here. Another one is, when we are having a D and a D here, this should be 0, because any number added to 0 will result in the same number. So value of E should be 0. So F and E are defined here. F is 1 and E is 0. So E is 0. Then we are using trial and error method. Putting 3, we get 3 here. We have to place 3 here. Likewise, we have to find other numbers. So this is a solution. Let us see, we have another solution. Yes, we have. This is another one. 6, 8, 0. 8s are repeated, 5s are repeated, 4s are repeated. F is having 1 and E is having 0. So these two are different. So we are getting a different answer. 1, 2, 2, 3 here, 1, 5, 5, 4 here. This will also satisfy this problem. This is another one. Again, the rules are obeyed and we get solution as this. This is yet another one. 9 plus 0 is 9. 8 plus 7 is 15. Carry 1. 1 plus 6, 7 plus 8, 15. The problem is solved in this case also. This is another example. This is yet another example, and this conclusions continues. This is not a good practice to have different solutions for the same problem. So we have to reduce the number of solutions. What to do? We have to add certain constraints. So let us add a constraint. For example, h should be twice that of O. If we have a value here, then this h or this h should have a value which is twice of O. Let us see whether this accepts or obeys that rule. No, because we have 2 here, we should have 4 at the place of 7. So this is violating the rule and we remove that solution. What about this? Double of 5 is not 8. So this is also removed. And here 3 double of 3 is 6. This is okay. So this can be accepted. What about this? 5 and 8 not allowed. 3 and 7 again not allowed. 4 and 8 this is also allowed. So the total number of solutions has been reduced to 2. It's our example. It can happen to be having more solutions, but with what we have done so far, we are available with 2 solutions. So we should again apply some more rules. We should harden the constraints so that we can remove one more from this. Let us see. This was our original set of solutions. We are adding this constraint because the first 3 digits of the result f plus O should compute to d. Suppose this is the constraint, then let us see what happens. 1 plus 2 plus 2 is not equal to 3, so this can be removed. 1 plus 5 plus 5 not at all 4, this is also removed. 1 plus 3 plus 3, it is 7 not 9, this can be removed. 1 plus 5 plus 5 is 11 not 9, this can be removed. 1 plus 3 plus 3 is 7, again not equal, this can be removed. What about this? 1 plus 4 plus 4 is 9, this is perfectly alright. So we are left with only one solution. So this should be our motto, to have a crypt arithmetic solution. We should be having only one solution for a problem because we are passing some important value by hiding those with alphabets. So that important value is 1449 as per this example. We should not have many values for this alphabet series FOOD. So these type of problems are called as crypt arithmetic puzzles. It's a part of CSP because it is having many constraints. We can remove constraints, we can add up new constraints as and when it is required, and we will be having many solutions at times, so we may have to add new constraints to reduce the number of solutions, so that we will be ending up with only one solution, that is crypt arithmetic.